Hello, and welcome to my talk, Iteration in Go. This is by me, Abram Hindle. I'm an assistant professor of computing science in the Department of Computing Science at the University of Alberta. Teach software engineering and stuff like that. This talk is licensed under CC by SA 4.0, and the code is mostly Apache 2. So this talk is about Go, and it's not really idiomatic. I didn't really know a heck of a lot of Go before writing this talk, and I didn't really know a heck of a lot after. Nathan at the Edmonton Go group gave a talk on the empty interface, and I wish I had seen that before I had made this talk, and so I revised the talk afterwards. So, what is iteration? Iteration is useful because it means that we can repeat tasks. Programming is useful because we can iterate. Iteration is one of the fundamental building blocks of most programming languages, and most programming languages that don't have iteration are annoying programming languages to use. We don't like using them. Iteration usually refers to repetition. In mathematics, iterating a function means to apply it repeatedly, whereas in programming, iteration can refer to any kind of method of repetition. So today I'm going to go over iteration in Go. The concepts I want you to watch out for are blocks and conditions. Blocks are chunks of code, usually the part that gets repeated. Usually they follow scope rules. A condition is an expression that evaluates either true or false according to what conditional blocks expect, and it's commonly used to determine if a loop continues. In Go, conditions usually are true or false. This isn't JavaScript or PHP where we have true-ish or false-ish. Other concepts that I'll be using are in-order execution, out-of-order execution, and dependency. Whether or not one value depends on another indicates if there is a dependency. Out-of-order execution is where you can get the same job done by executing in any order. And in-order execution is ordering basically executing in an ordered sequence. So the first thing that really surprised me about Go was the lack of a while loop. In fact, they just dropped the while keyword, and they just let for do it all. Makes sense. What while loops usually are used in other languages for is to repeat a block until a condition is met. That is, you've got a block of code and you want to repeat it until the condition is met. So if we look at this block right here, I start with condition equals false, and then we go while condition is true, set condition to not equal to not itself. So this block will never run. Why? Well, because condition was false, so nothing in this block will run. But if condition was true, this block would go, oh, condition is true, I'll run this code here, and then condition equals not condition, so not condition is false, it comes up here, it sees false, comes out of the block, and ends up around here. This block is dependent on condition, and so is this condition dependent on this condition. All right, so a common use of a while loop is to repeat until something is met. So here we use an infinite loop. We go for, and we've got no condition, so it just loops. And we go, while this is true, reads plus plus, so increment reads, and then read a string, and just throw it away because we don't care what the value is. If we've got an error, then we break. Break allows us to break out of the for loop immediately. It'll go right about here. And then it'll break out of this for loop, so we'll end up here. And then we can print out the results. This will print 1 regardless of how many lines this will print at least 1. So it's just how many times we tried reading a string. That's really what it means. In this case, I've got x equals 10, and I got x greater than equals 0, and I say decrement x each time. So this loop will run about 10 times, and eventually x will be 0, and when we print it out, it'll print x equals 0. One thing to note is this block depends on this x. This block depends on this reads. So the value of reads is important to this block. It actually has to read it to increment it. Then another reason you might use something like a while loop is when you got to loop over a few things many times and you don't know how many iterations you need. So in this case, we got y equals 100, and then while y is greater than 1 divided by 3. This loop will run a bunch of times dividing by 3, so we get like 33 and things like that. All right, so back to this loop. So we got y equals 100, it divides it by 3, we're at 33, it divides it by 3, we're at 11, we divide that by 3, we're at about like 3.6, 3.7. We divide by that by 3, we got like a 1.2. We divide that by 3, and we get a 0.4, right? So eventually it stops, but we don't really care how many iterations it makes. We just have a condition here that it stops right there. Now, each version of this loop is actually dependent on the old version. So you see y equals y. It means that every time this block runs, it's dependent on y. Furthermore, for this calculation, it's got to be done in order, and it depends on y. All right, so those are the while loops. For the for loop, we want to iterate with a condition over a collection of elements, usually, or over a space. So here we've got sum equals 0. For I equals 0, I less than 10, I plus plus. We add that to sum. It'll print out 55. This one didn't show up. This is a bunch of Unicode characters. This is a string. So we have a string. We got a slice of strings. We got a map of string to string, so A to A, B to B, C to C. And then if we want to iterate through V is this this string slice. We can go range. And what range will do is it gives us the index, which is pretty nice. So it'll be 0, 1, 2. And it gives us the val. So it'll be 0, A, 1, B, and 2, C. All right? So then we get those values in this block. Then what we do in this block is we go for j equals 0, j less than equal to I, j plus plus, and we concatenate S with the value, so A, B, or C. So this block here is dependent on S, and this block here is dependent on V, the values of V, but it doesn't care what V actually is. Unlike this block, which actually cares about the last value of sum every single time this runs. And this one probably needs to be in order. You can do it out of order, but you want the values to be concatenated in order. So what this will print for this one is it should print 1A, and then 2 B's, and then 3 C's. Okay? So if we just go and check what the value is, different one, we can see that we'll get A, B, B, C, C, C. Right? That's what gets printed out. Right there. Okay? So we can also iterate over more complicated collections like maps. So with a map, our range will give us the key value pairs. So here we take the string S and we concatenate key and value to it. So what happens is we have we've got the old string right there, but then it goes key, value, key, value, key, value. Okay? So we can iterate over collections that way, which is pretty nice. This range function is pretty flexible. We can also iterate over strings. So if we look here, we've got the string S2. Now, S2 doesn't show up here, and I'll show you what it actually is. S2 is the string. It's like your Lucky Charms of Unicode. So we got S2. And it goes I, and I is the byte location in the string, and val is the ruin. So the ruins of the string are returned. These are Unicode characters. And then we repeat them. So it concatenates a big string. So instead of just being A, B, B, C, 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 it actually increases a lot because this I is a byte location. And let's just go look at what that was. So we see we have our old string right here. Now we got 1 heart, and we got 4 suns, and we got 8 stars, and we got 12 umbrellas. I think 12 or 16 hearts, and then a bunch of knights, and it just keeps going up and up and up and up. We can up by about 4, I think. And we can see by the end of it, we've got a lot of nuclear symbols. So the code points, or the locations here, will be where in the string it is. So just watch out. Range doesn't always return what you might expect. Okay? So the for loop allows us to iterate over ranges of numbers, allows us to iterate over lists and slices, allows us to iterate over maps, allows us to iterate over strings. So that's pretty handy. One method of iteration that you can do in Go is recursion. You might want to use recursion for this kind of data structure. So this is a data structure where each tree has a value, but it also has a bunch of branches, and those branches are basically composed of a map where we've got the branch has a name, and then the branch has a tree. So A is a tree, B is a tree, C is a tree, D is a tree. We also have stumps, and stumps are basically a branch that doesn't have any children. It's just an empty map. So here we got A, tree 1 stump, B, tree 2, and then it has a sub branch here. And you can see that we got numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? This kind of data structure is hard to iterate over with one single for loop. So really what we want to do is we want to iterate it over recursively. We want to be able to access every single element here, and the easiest way is to use the stack to store our current state such that we can come back to it. So first off, our tree structure in Go, pretty simple. We have a value, it's an int. We got branches, it's a map of strings to trees, so they're named branches. Our tree sum method is very simple. It's tree sum, takes in a tree, returns an int. Start the sum with the current value of the tree. Then for each branch, we ignore the key name. And there's no point. They're named branches, but it doesn't affect the sum. So we can go sum plus equals, so increment sum by tree sum. This tree sum. So tree sum calls tree sum. So it calls itself on itself. And what happens is for every single tree, we'll get this tree value, and all their children will be added to the sum, and then we'll finally return that sum. So if we had a tree that didn't have any branches, it would just return sum equals tree value right there. This block wouldn't run. So what's important to note here is the only real dependency here is the tree. We don't take in sum or anything like that. This sum is local to this block. It's modified by the return values here. This recursion also lets us do pretty neat stuff. So we could even walk a tree. I just want to show you how we can call tree sum. So here we got printf tree sum tree, right? So it's going to print that out. Let's see, where is it? Tree sum 55. So we had from 0 to 10. The sum of 0 to 10 is 55. All right. Here we've got tree walker. Tree walker takes a tree, and then it takes this other parameter. It's a function which takes a tree as a parameter and has no return value. So the way tree walker operates is it runs a function on that value, and then it goes to the branches and it runs tree walker there. So this is basically like this should be depth first search, not breadth first. Anyways, so this will go throughout the entire tree, printing out or applying the tree to this function f. So it'll allow us to walk a tree. This means we can do neat stuff like take the tree, and then we can pass the tree in, and we can then print out the tree value. So we can just pass in this function right here, right? And then it can walk the tree for us. So this tree walker will be pretty useful. The output of the tree walker is node values, all these node values, right? So it's going 0, 1, 2, 8, 9, 10, 3, 4, 5, 6, 7. And does that match our tree? Well, let's go look. So we have 0, 1, 2, 8, 9, 10, 8, 9, 10, 3, 4, 3, 4, 5, 6, 7. So what's interesting is the map kept its order in this case, and we managed to walk through the entire tree. All nodes were visited. Okay. So that was recursion. So we can walk a tree and we can iterate over a tree using like a tree walk, and we can rely on functions to actually operate on that tree. So I was going to cover iterators, but one of the neat iterators in Go is the channel iterators. So we use the channels and the Go routines to basically use like a coroutine to iterate over something. So because I can't add methods to built-ins like int, I have to make my own type called iint. So here we've got a function. It operates on an iint, which we'll call max, and it has an iter method, and the iter method returns a channel of iint. So that means we can actually use range, because we can use range on channels, which is pretty nice. So what do? We make a channel. We make a Go routine. This Go routine goes from 0 to m, incrementing, and it outputs those ints, those iints, to the channel. And then once it's done, it closes the channel. And this Go routine is forked off, and we return the channel itself. So the way we call that one is pretty simple. We just go for I in range, do that. Note how for channels, the for loop only has one element. That's just what's getting returned. And so we'll just print out wow. So for iint 6, let's see what the results are. We got wow 0 to wow 6. So we've got a inclusive range. Okay, pretty neat. You do take the hit of running a Go routine, but these are very nice, and it means you can have complicated for loop logic and just emit from inside, which makes things pretty easy, makes it easy to reason about it. So we can use this channel iterator to traverse more complicated data structures. So we can actually make a tree iter. So tree iter here takes in a tree and returns a channel that emits trees. Okay, so it emits trees. That's pretty cool. So then we go make the channel, a channel of trees, and then our Go routine takes a tree walker, takes the tree. Remember tree walker? I'll just show it to you again. Tree walker's right here. Takes a tree, takes a function, does something on it, returns nothing, right? So the tree walker walks the tree, and then for every tree element, it emits that tree to the channel. Once the tree walker is done, it will close the channel. So do you see this? We can compose really neat things, really simple recursive iteration, right? We can take that, we can use it to compose with Go routines and channels, and we can make something that walks an entire tree. What it means is that we can actually use the tree iter, right? We can go ahead and use the tree iter to walk the tree. So here's how we walk with the callback walker. But the tree iter allows us to use range, and now we can go through every tree element of a tree in a linear order, which is really neat. So this allows us to basically serialize in the strict definition of serialization, as in order, printing it out in order, allows us to serialize a data structure that is arguably not linear and not necessarily serial. It's pretty neat. So we're using Go routines, and we output trees. And this thing will go now via iter node value, and let's just go look at the result. And here it is. So it does the same thing as tree walk, and shows it. Pretty great. So channel iterators are useful, but you're going to take a performance hit probably. In OO, the iterator pattern is a pretty common pattern. You've probably used it before. You probably had methods like hasNext and then next method that returns a value, or you've got a next method that says if there is a next element and it changes the state of the iterator and then returns a value. What an iterator really is, it's an object that keeps the state of a iteration through a collection. So here we've got string iterator. We got type struct. It's a struct, it's a string iterator. We have a current location, and we have a set of runes, okay? So we convert a string to runes, and then we can iterate over it. So here I've defined a way to make this. So we go func iterator. So we're going to make a new iterator, and you give it a string, and it returns a ref to a string iterator. And that ref is -1 for current, so it doesn't start anywhere. And then we convert the string to runes. And I got some of these iterators from this guy over here. He's pretty clever. Then we assign a next method. The next method returns bool. Bool will tell us if there is a next element. So what we do is we increment our position in this slice of runes, and then we return to see if we're over the edge of it. So if we're not over the edge, it returns true. If we are over the edge, it returns false. To get the value out, we simply access our list of or thing of rune or our slice of runes, and we get the current and we stringify it. Okay, so pretty simple, and this allows us to iterate through a string. Although you had the range function at the same time, so you're like wondering why bother. Nonetheless, this is an example showing another method of iteration, and what I'm saying is you can use object-oriented patterns like the iterator pattern to iterate through things. You can also use these iterators to do custom flow control. For instance, maybe you only want the even values, or maybe you only want the even indexed values from an array, or from a list, or from a string. So here is even string iterator. It looks pretty well the same, except that we, instead of going plus plus, we go plus equals 2. This means that we can iterate through a string. So we got that string S. Remember, it's built up. It's now full of Unicode. So this first one allows us to go string val, and then we just print the string. The second one, we use an even iterator on the string, and we do that. Notice how the for loop is simply a for loop with condition. This is basically your while loop. So we're basically like, while there is a next element, or for next elements, print, and just get the value. Okay? So what does that look like? Well, it looks something like this. So the first iterator, just a string iterator, we get these. It just prints everything out, string value. And then it's pretty long, so I just want to hammer this in. So So we're from line 39 all the way down to, line 167, about 130. So look how few these are. So we're at like 170, and we go down to 230. So that's about 60. So that's about half. So our even iterator lets us skip over half the values. That's pretty handy. So you can do arbitrary flow control with objects. Okay, I want you to check something. Do you notice in the prior examples there was order? In the iterators, they were in order. The tree walker was a set order. This iter function was in order. Think about the tree. If we're actually just getting the sum of all the values of the tree, does it matter which order that we actually evaluate the tree in? So because we can do sum in just about any order, we could actually exploit that. But just think about that. So not every computation you do actually needs to be in order. So now I'm going to introduce the map function. Map does not come with Go. Map comes with a lot of other languages like OCaml, Haskell, Perl, Ruby, Python, I think Java now, and C# now, and everyone's got map now. Anyways, what map does is it's iteration in mathematics, basically applying a function, applying it repeatedly, and applying it to every element in a collection. So here we've got the basic version of map. So we take map, we take a function, we take a list, and we go, we'll produce a new list where the elements are f of a, f of b, f of c. So every single element here has f applied to it, this function, we get it up. So if we say applied the square function to a list of 1, 2, 3, we get the squares of 1, the squares of 2, and the squares of 3. So 1, 4, 9. 3 squared, 2 squared, 1 squared. Okay? So it does return things in order, but if this function doesn't depend on any aspect of this list or any other state, then we could actually, it wouldn't matter which order we applied the function in. We could have calculated the 3 squared first, and then the 1 squared, and then the 2 squared. So we could have gone 3, 1, 2, or 2, 3, 1, or 1, 2, 3. So the order actually doesn't matter as long as our output is ordered. That's sort of interesting. So what does a map look like in Go? Well, turns out you got to build it yourself. So here's an example of an integer to integer map. We have an array or a slice of ints. We have a callback, and this callback is of type int to int. So one int parameter, an int return, and then this whole function returns a slice of ints. So what we do in the function is we make a new slice. We then iterate over our array using range, and we use both values, the index and the value. We apply the value in the callback. So this is your f. Apply that, get the value, put it in out, return out. Now, what if we wanted to do another type? Well, for string, we got to do the same thing. We're basically repeating code. It's totally uncool. Mostly because the type system doesn't have generics, so it's pretty awkward. How can we use this? Well, let's look at int and map. So let's make this slice of ints from 1 to 8, and we got inc and we got square. Inc takes a value and returns that value plus 1. Square squares a value. So we go v3 equals int map v2 inc. This is v2, and we pass the inc function. So then it will apply that. It'll produce a new list. This slice will be independent of this slice. This slice will not get mutated. And then we can do it for a lack of generics, or we can do it for the square, and we can get the square of v2. So let's go look at the output of that. So inc of v2, the input, and the output. So 1 to 8, 2 to 9. So everything plus 1. For the square, it's 1 to 8. For the output is 1 to 64. Okay? We can also use it on our strings. So we can use our string map. We can make a function called base name that will return the last bit in a path. Just give us that base name. So we take these paths and we go stir map, our list, and the base name, and then it returns the base names. Let's go look at the stuff. And it converts this list into this list. So home, file, local. Okay? And now let's look at this example. We're using HTTP GET. We're doing gets. We got a status. And then for every URL here, we're doing an HTTP GET, right? So we're going to go stir map, URLs, status, get the statuses of these, print the statuses out. Right? So we get 200 OK, 200 OK, 200 OK. So everything was OK. We managed to get them. But think about this. Who runs cbc.ca? Who runs gc.ca? Who runs alberta.ca? Are these on the same servers? Well, this might be the provincial government, and this might be the government of Canada, the federal government. So maybe they're separate. And this is the CBC, the Canadian Broadcasting Corporation. It's supposed to be separate from the government. These might be on different computers. If they're on different computers and they're not talking to each other, they're probably independent. This means that we don't actually have to wait for cbc.ca to finish before we get gc.ca, and we don't have to wait for alberta.ca. The order that we get these in doesn't matter, and we don't have to wait for either thing to actually end. So this strictness that we've enforced here, doing this in order, doesn't really matter that much. These are independent inputs. This is an independent function that has only one requirement, which is URI. It's not a closure. There's nothing funny out here. It's not relying on URLs or anything. So that means that we could technically apply this function in any order we wanted to and still get the same results. The output of that looks like 200 OK right there. Okay, so think about that. We don't need to do these in order. And why do we have to wait for cbc.ca to get gc.ca? Wouldn't it be great if we could do them at the same time? Well, one reason people like the map function is it's easy to parallelize. The idea is that the function you pass in the map doesn't have a lot of state to it, so you can apply it in parallel. This is because you limit the dependency of a block in order to actually run it. So here we've got int map, and we pass in a array or a slice of 1 to 1000, and we ask it to be squared, and then we sum it. So we get the sum of squares. We can parallelize this with our parallel int map, same kind of thing, and we can say use for workers, and then we sum it. Okay, so if we wanted to go to, there it was. If we wanted to go to that, we could go make. See, there's the sumRes functions. If you want to set Go to use more procs, more processors, we can go export for, go make, and then it'll try to do this a little faster, which is pretty nice. But you can't really see it here. Okay, so it doesn't really matter. Int map or parallel int map, these could be the same function. Semantically, we just want all the squares of these returned and then summed. Okay? So what we can do is we can make int map. Furthermore, we can take I/O, which is inherently slow, and we can parallelize it. So for the I/O, it makes a lot of sense, especially even on a single core machine, because the I/O is just going to block and take up a bunch of time compared to the CPU. So we could then get all these URLs in parallel. So how do we do this? Well, here's our parallel int map. We take a list of ints, we take a function of int to int, and we take a number of workers. We make a bunch of channels based on how many workers we have. Unfortunately, the make here doesn't actually initialize our channels, so we got to go ahead and we got to make the sub-channels. So we go and make all the channels. You could actually move this down in here, but I don't feel like it. Then figure out about how much work to send to each worker. And then for each of the workers, we send it a slice. So I'm sending it basically a unit of work. So if you got 4 workers, it cuts your list into 4, and we produce this slice down here as sublist. Okay? So this is the same code again, sublist. We're making the sublist. And then what we'll do is we'll pass it into this par function. And this par function will take our channel, and it will output our int slice to that channel after we do int map. So we'll take our new sublist, right here, see this sub L, and it will get put into here, and we'll apply the function that we passed in, and we'll output that. We'll emit that to a channel, then we'll close that channel. And for each worker, we'll start off this parallel function. So it will basically, each worker will run an int map. Then what we'll do is we'll join everything. We'll make an output slice. That's the size of the input, size of that. We make the output slice, and then we'll go for all the workers. We'll read from the channel. And then we'll copy into our output slice. We'll copy the output of that channel into the output slice. Then once we're done, we'll return. This will be done in order because our workers are in order. And if the first worker takes a long time, well, we needed all the output anyways, so it's okay. We'll just wait on it. So we wait on the first worker, then the second worker, then the third worker, then the fourth worker. 2, 3, 4 might be done before the first worker is done, but that doesn't really matter. We copy them all out into our array, and then we return it. So that's just a parallel map. It's pretty simple. All we do is we use channels for parallelism. We use Go routines for the parallelism. We split the list into that many workers, and then we parallelize it that way. Okay? So that allows us to make these parallel calls. So stir map is going to be pretty similar. Another method that's really important in functional programming and is like the sister method of map is the reduce. Reduce is linear. It's one at a time. Basically, you collapse a collection down to a single value via a function or an operator of 2 arguments. So what you do is you take either your first 2 or your last 2, you apply f to it, and you get a value, and then you apply that value to the next f and the new value. So we go f of E99 and this result. Okay? So in the case of add, what it'll look like is we'll have add 1 plus the addition of the rest plus the addition of the rest. So basically we'll end up doing that many sums, and that many sums will end up being, or that many adds, and that many adds will turn up to be a sum. Basically, sum is a reduce. So here we got a list of x, and we got iadd equal is a function that takes in 2 parameters and returns an int, and it just returns x plus y. So to produce the sum of something, we can go int reduce, and we can go vex, so 1, 2, 3, 4, 5, 6, 7, 8, 9, iadd, and it will sum it together. So our int reduce is very simple. We initialize an initial value. I like to use O because for me, O means old. So that's the old value. We get the length, and then we start at 1, and we go throughout the slice, and we apply our callback, that's an int to an int. We apply that callback to the old value, the new value, and then we set the old value to be the output of this. Then we return that old value. So this block here is dependent on this O here, and it mutates it every single time. Then we finally return it, and this is done in order. So the reduce is like a map, except it produces one value. A map produces n values for n inputs. This takes 2 inputs, a list of n values, and a function, and then it produces that. So reductions can also be parallel sometimes. So if you have a problem and it can be broken down like a summation, you could actually just break it down and then apply the reductions on the separate parts and then reduce again. So some problems actually lend themselves to multiple reductions. So what we could do is we can combine it with map and reduce. So what I'm going to do is I'm going to provide a mapper and a reducer and an input and how many workers, and it's going to calculate that. Notice how this is a lot bigger number than the one before. So what does our parallel int map reduce look like? Well, we got to have a mapper function, we got to have a reducer function and number of workers. This sort of looks the same. We initialize those channels. Then what we do is instead of just calling int map, we call int reduce, right? Call int reduce on it. So it calls the mapper function, and then it calls the reducer function. And then we just emit that. And then our reductions are the same. It looks similar, but watch here. So we get a list of reductions, and it's the number of workers. So for every worker, we get one value, not many values, just one value. Then we call reduce again on those reductions, and we pass in our reducer. So we basically get, in this case, we'll get a couple of large sums. We'll get 4 values, and then we'll call sum on those 4 values. So it gets done. The final reduction is not parallel, but there's a parallel reduction for every split of that list. We can do this because the problem is easily modeled as a tree. It has commutative and associative aspects to it, and it can basically be modeled as a tree of computation. We can break off the branches, and they can be executed in parallel. And we can do this because there's a lack of dependency. For instance, in the case of sum, we don't have to send like sum equals 0 down to each branch. What we can actually do is we can initialize a sum to be the sum of the branches below us. So we can keep aggregating sum up instead of passing data down, which is actually quite useful. By having a structure like this, it means you can break off any of these branches and you can run them as like a separate worker. So if you can think about your problem as a tree of computation, you can probably parallelize your problem pretty well by finding branches in that tree that you can break off. All right. So when I was doing this, I was bothered by making int maps and things like that. So what I thought I'd do is, well, I could make a map interface. So Go allows us to use interfaces. So I thought, I'm going to make a map interface, and it's going to allow me to take a slice of ints, and it's going to let me produce any kind of output. So what I did is I made this method. This method's on ints. I define ints as a slice of ints, and it's called map, and takes a callback of E to E. Now, E is type E interface with nothing. It's a blank interface. And my map is a blank interface. So our mapper interface is map with a function that takes a blank interface to blank interface and produces a slice of blank interfaces. The reducer was going to look pretty similar. It's going to be a function that takes in two blank interfaces, produces a blank interface, and returns one final blank interface value. We could have saved typing in these blank interfaces all the time just by using our type E here. And that's the E that I'm referring to here. So this is blank interface, blank interface, blank interface, blank interface. So our map looks pretty well the same. We make a slice of blank interfaces. Then we apply this callback V. It returns a blank interface, takes in a blank interface type object, and we assign it to out, and then we return out. To call it, what we'll do is we'll first take our list of ints, vex, we'll call it ints. So this is just coercing the type. And then we go .map, and we pass in a function. Unfortunately, this is the ugly part. Our function takes in a blank interface and returns a blank interface. So because this isn't an int, I have to coerce it down to an int. So I go, x, you're an int, +1. Okay? So this will completely fail if x isn't an int. But what's nice is I don't have to care too much about the type of the return value. The return value will be accessible. It will be a blank interface, but I'll be able to access it. So what I'll do is I'll say generic map of evex, the return value here. Let's just print it. So what happens is, since this is an increment, it goes 2, 3, 4, 5, 6, 7, 8. What I want to show you about this neat function is that since it can return a list, right? A list of blank interfaces, it can return any type. So watch this. We come in here, we take an x. We know that this vex is full of integers, but we convert it to float 32. So this is convert the type to float 32 after we get the integer representation and add 1.1 to it. So it's like the increment except we added 0.1 to it. And you can see here the result is float 32s. We get floats out. So this function is actually very powerful. It allows us to output slices of the type of the return value. So that's pretty nice. So we gain a little bit with the type inference. Unfortunately, we'd have to do the same thing for string, right? So what I wanted to do was I wanted to basically make a generic map that would convert collections, so lists of blank interfaces, empty interfaces, convert lists of these to other lists of them. So basically collection to collection, right? So I wanted a map, I want to give a callback, goes E to E, so empty interface to empty interface, produce a list of empty interfaces. So this is all fine and good, but you got to ask yourself, can we actually call this? The answer is there is a problem. The problem is that if you have a slice of strings, it's not the same as a slice of blank interfaces. This isn't a blank, this is a slice. This isn't a blank interface. This whole thing is not two parts. It's one part. It's one type, a slice of blank interfaces. You know what it's not? It's not a slice of strings, and it's not a slice of ints. So that's problematic, isn't it? It means that we need to pass in, if we want to call the map method, it has to be a collection of blank interfaces. That's the only way we can use this, because this is a special type. Well, it's not a special type. This is just a slice. That's all it is. You know, Go doesn't care that this is a blank interface. What Go cares is that this thing is called a slice of blank interfaces. Okay? So this means we have to make a slice of blank interfaces, which is awkward. So what we have to do here is we basically have to make a collection. So here I got svx is a string of a slice of strings, A string, B string, C string. And to be able to call that method, I've got to make an empty interface slice. So I've got a function that I've called collection. And what it does is it converts a list, like a slice here, to a slice of empty interfaces. Then we can call map on it. And our map still has this ugly notation where we have a value x of empty type, produces empty type, and then we have to coerce everything and cast everything down to what we expect it to be. But nonetheless, it allows us to work. So for let's see, generic map with string. We're basically concatenating two strings together, doubling them. We get AA, BB, CC. So that's string to string. The cool thing is we also gain that genericity. We can do strings to ints now. So we can go len x string. So that's 1, 1, 1, because A, B, C, right? You see A, B, C. All their lengths are 1. Okay? We can do the same thing with our ints as long as we cast them. But we need to convert them, unfortunately. We need to convert them to a collection, a slice of blank interfaces. How do we do this? Well, I found this Stack Overflow post that was very helpful, and this is a simplified version of it. We use the reflect module. What I say is collection takes a slice of stuff, and look, it's not a slice. I just say a blank interface. So I'm saying it accepts something and it expects it to be a slice, right? So this is danger zone, right? I'm not saying a slice of stuff, I'm saying anything. And it's going to produce a collection. So what it does is we go reflect value of slice of stuff, our slice. And then we act like it's a slice. So we go our slice length, and we produce that output array, that output slice. We go I equals 0, I less than our slice length, I plus plus. And then we go get the element from there and get the blank interface version of that and plunk it into out I and return out. So it's like our map. We're basically mapping our values to blank interfaces, right? It's a little bit awkward. This is needed because basically our blank interface is like a struct that has two elements in it, and one element will be the thing you wrapped up, that interface type, as well, or that value, and then also the type, the blank interface. So it's pretty annoying. So what happens is we use this collection method, and we can write our map very simply. So we go, we can make a map method that takes a collection E, takes a callback, returns a collection of empty interfaces, and all we do is we take this. Notice how it's not this. This is just an empty interface. We pretend this is a slice, and we'll map it. So this thing is going to break at runtime if you put the wrong thing in it. Also, it's got to wrap everything up. We can write our reduce pretty well the same way. So here's our generic reduce. We take in a collection. It goes E to E to E, and it outputs an E. So we go O equals, initialize it with that value, and then go through it all, finally return O after calling our callbacks and getting all the output. And then our generic reduce is just collection of this empty interface. This is a hack I really don't like. This is not type safe. It sort of ticks me off that I have to do this, and it's not very fast. And then we just call reduce on it. We just call reduce as a method. So that's pretty neat, right? So this means we can do generic map reduce and go. We could also do it with parallelism if we wanted to. We could go and port that ugly int, or that ugly parallel int map and int map reduce. We could go port it to this kind of thing. But quite frankly, the whole affair of dropping type information and abusing runtime reflection to be able to pull this off turned me off of it a bit. And the whole point of using the parallelism would be that you probably wanted to increase performance. So this would not be a performance increasing kind of deal. Nonetheless, it's pretty neat that you're able to pull it off and go, and it's relatively safe. But at the end of the day, you still have to pull those values back, right? Because they're all empty interfaces. You got to pull them back to something useful. So how do we evaluate it? What does it look like? Because I've just been showing you the code, right? So how do we actually apply it? So here we go map, we put in any value we want. So I'm going vex. Remember what vex was? Do you? Vex was, it was back here a little bit. Nope, not there. Vex is over here. It's just an int slice 1 to 9. So we go to vex, and we say, I've got this function, takes empty interface, produce empty interface. We get the int version of it, and we square it. So slow map res will be the square of vex. So it will produce 1, 4, 9, all the way to 81, because that's 9 times 9. We can also do slow map reduce. So here I take the output of this mapping and I reduce it, and I use a reduction that's just sums. So it will give me the sum of that, which is 285. Okay. So we can use this generic reduce. Now, the reason why I have this as a function is because then I can take that empty interface and I can call reduce on it. And what you should know is every time I pass this in, it's calling collection on it, right? So it makes a collection. This is a cost, and you have to garbage collect and throw away, and it's a big waste of memory. And then it calls map on that new collection you made. Remember, this collection we called make, so there was allocation involved. Nonetheless, we get a generic map reduce. There's probably better ways of doing this. I don't know Go very well, but I knew enough Go to pull this one off and be able to Google it pretty hard and be able to work it out. Nonetheless, it's pretty neat. You can pull this off. Easier functions to pull off would be things like an each, like in Ruby, an iter or an each, where you just say, hey, collection, apply this closure to every element in there, and it returns nothing, so don't worry about it. But there's not a lot of point doing that in Go since you already have the for loop and the range method, or the range function. So what's the point? Now, I've covered a lot of things. I've covered the for loop, the iterator, the range, recursion, map, reduce, and generics, but I also covered generics at a cost. The generics came at a big memory allocation cost, reflection cost, lots of extra work. Nonetheless, one takeaway that I hope you get from this, especially the parallelism portion, which is actually very nice in Go, is that reducing dependencies and blocks allows iteration to be parallelized. You should consider order or strictness if they are actually needed. Look at your problem. Does it have to be done in order? What's cool about this kind of stuff is that these concepts apply to other languages as well. Now, before I finish off, I just want to show you, so let's do this, Go max procs. And the HTTP requests are sort of getting in the way. Let's get rid of them. Go. So HTTP. So we got URLs. All right. So I'll just go comment that out. URLs. Get rid of this parallel get. Right. None of those problems. Should work. Might have to block this out. All right. So that should work. Let's just try it. No, I messed up. I forgot that I'm using Go, so I had to do this net thing. Okay. All right. So we're getting about 0.9 seconds for our really big map reduce. So if I set the max Go procs to 1, what happens? 1.2, 1.2, 1.2, 1.2. I'll set it to 4 again. Let's run it again. 0.9, 0.9, 0.9. So you can see I gain a little bit in terms of performance from this genericity. Or not from the genericity, from the parallel map reduce. I'm not convinced that the generic stuff is going to run very fast at all. All right. So I hope you enjoyed the talk. All this stuff is on my GitHub. It's in the Python iteration talk on the Go thread. I'll just link to it on the YouTube and all that. And if you have any questions, feel free to email me. My email's at the front here, abram.hindle@ualberta.ca. And I hope you enjoy Go. Another thing I got to bring up is I couldn't do this alone. There are a lot of resources I relied on. I relied heavily on the Go spec. But Eleanor McHugh has this really excellent talk, which you should go watch right now, Going Loopy, Iteration in Go. And I had to swipe a whole bunch of ideas from her talk. So I really recommend watching her talk, and her slides are annoyingly at SlideShare, but whatever. So go watch her talk. And I relied a little bit on Stack Overflow. And for iterators, there's the Go language patterns, as well as this really excellent blog on Go iterators, as well as there's a discussion on mapping Go. My Mapping Go is available for you to download and use if you want to. It's on the GitHub. All right. So please go check out these resources and try to iterate in Go and try to use higher order functions and all that kind of stuff. So functional programming is, yeah, quite possible in Go and quite possible in Go in parallel. Pretty neat. All right, I'm done rambling.